So this is on page 13. We are going to talk about one-sided and two-sided limits. Now we have seen this notation before when we were in around chapter 1, where we are talking about the limit as x goes to a number from the left hand or the right hand side. And hopefully you recall that the negative means from the negative side. So what it's saying is the limit as x is going to c. Now when you're talking about a graph going to c, there are two sides. Are you going from the right or are you going to go from the left? And that negative means from the left. So this is the limit of f of x as x approaches c from the negative side or from the left side. Okay, and then so likewise, this one with a plus means going to c from positive side. Now the theorem says if a function has the limit, then that x is approaching c from the left and right, and then they are actually the same value. So a function f of x has limit as x approaches c if and only if the left hand and right hand side limit as c, first it has to exist and second are equal. Okay, what does that mean? Okay, graphically this is what you're looking at. So let's look at two separate situations. One is that you have a graph like this. There's a jump at c, and the other one is that they're connected at c. So the limit theorem says the limit as c exists. Okay, limit as x goes to c of f of x exists if and only if is a very strong statement in the math world. If and only if the left hand side and right hand side limit at c exists. Okay, so the question is does the limit as x goes to c from the left hand side exist? Yes, right here. Does the limit as x goes to c from the positive side exist? Yes, right here. So that's the first condition. It has to exist. Left hand side and right hand side limit has to exist. Second thing says it has to equal. Now are these equal? No. So then the limit as x goes to c of f of x does not exist for this graph on the left. Now for this graph on the right, let's look at it. Limit as x goes to c from the left hand side. So as graph is going to c from the left hand side, does the limit exist? Yes, right here. Does the limit from as x goes to c from the positive side exist? Yes, right here. So that's the first part. Does the left hand side and right hand side limit exist? Yes, they both exist. The second thing is, are they equal? Yes, they are equal. They're approaching the same value. Therefore, limit as x goes to c of f of x exists. And then whatever that value is, you would say that that is the value of the limit as x goes to c. All right, so to prove that a limit exists, you have to say that the limit as x goes to c from the negative side of f of x is equal to the limit as x goes to c from the positive side of f of x. If they are the same number, then limit as x goes to c of f of x is equal to L. Okay, so if this happens, then this happens. What does it mean if the limit from both sides are not the same? It means that this function is discontinuous. Okay, as you can see from this first graph here, it is disconnected and there is a jump discontinuity. All right, so let's look at some functions. We're going to do this both ways, graphically and algebraically. So we have this piecewise function, and the question says, let's find the limit as x goes to 2 from the left-hand side and as x goes to 2 from the right-hand side. Okay, so let's take a look. This function is going to be a parabola that points down. You want to put in some values. I am going to just show you what the values are, but you should kind of try it yourself. Okay, so looks like this. And then if you remember from before, graphing a piecewise function, if it has an equal sign here, that means there is a value at the actual x equals 2. So then we want to put a solid dot. This one that doesn't have an equal sign, that's a greater than. When we draw it, we're going to have to put an open circle because there's no value there. Okay, so we're going to draw this like this. All right, so the question is, what is the limit as x goes to 2 from the left-hand side? All right, let's trace this graph from the left. So from the left, that is this part, we're going to 2. And you can see that when you go to x equals 2, the graph stops at 3. So then this value is 3. Okay, limit as x goes to 2 positive. That means from the positive side. So we're going to trace this graph from the positive side of 2. And then once it kind of gets to 2, the limit stops at 1. Now you might say, same thing we did in class, that why is this the limit if there is a hole? Remember, limit is when x is approaching that x value. It doesn't have to equal. Of course, there is no number at 2 from the right-hand side, but this is approaching 2, so then it doesn't have to equal, which means it's just trying to get to y equals 1, even though there is a hole at exactly 1. Okay? All right, so we just had to solve this one. Now, if they ask you another question and ask you, what is the limit as x goes to 2 then? You found the left-hand side, you found the right-hand side. Now, what is the limit exactly at 2? Well, remember the theorem we just talked about? So the limit at 2 exists if and only if two things. 1, left-hand side, right-hand side limit exists. Correct? We do have those. Second, left-hand side, right-hand side limit has to equal each other. It does not equal. So then this, we would say, does not exist. All right, now that's great. We don't want to draw this out every single time, so let's do this algebraically. I'm going to change this to a different color. Algebraically, limit as x goes to 2 from the negative side. Going to 2 from the negative side means we're coming from numbers that's smaller than 2. So then like from 1 and 0 and -1, so all this numbers smaller than 2. So that is this part. X is smaller than or equal to 2. So then you're just going to plug it into this one. Well, what is that? That is f of x. So what we're doing is trying to find the limit as x goes to 2 from the negative side of this function. So all we have to do is just plug it in. So -2 squared plus 4 times 2 minus 1. So this is -4 plus 8 minus 1, which is 3. And you can see that that is exactly what we found when we did this graphically. All right, now let's do the other one. Limit as x goes to 2 from the positive side From the positive side means we are looking at numbers that's bigger than 2. So that is bigger than 2. F of x is this 2x minus 3. So this is limit as x goes to 2 from the positive side of 2x minus 3. So then we just plug it in. So 2 times 2 minus 3, that is 1. So you can see that we can do this both graphically and algebraically, and they will give us the same answer. So let's practice without graphing. What is the limit as x goes to 1 from the negative side? And then what is the limit as x goes to 1 from the positive side? So you want to pause this video, give it a try, and come back and check your answer. All right, so this one, limit as x goes to 1 from the negative side. 1 from the negative side, we're using numbers that's smaller than 1, so we're going to use this function. Okay, so that is x cubed minus x plus 1. Okay, plugging it in, 1 cubed minus 1 plus 1, that is 1. Okay, from the right-hand side, we're going to use this part, so that is 5x plus 1. So limit as x goes to 1 positive of 5x plus 1, we're going to plug it in, so 5 times 1 plus 1 is 6. So that is it. If that's all they ask, find the left-hand side limit, find the right-hand side limit. If they do ask an additional question and said, what is the limit as x goes to 1 of f of x, what are you going to say? Remember that the theorem again, if you want to figure out the limit at a point, it has to have two things exist. So the limit as x goes to 1 exists if and only if two things. 1, left-hand side, right-hand side limit exists. It does. 2, limit the left-hand side, right-hand side limit goes to the same number, which it doesn't. So then this does not exist. Now let's look at another type of question. This next question says, find limit as x goes to 3 of f of x and prove that f is discontinuous at x equals 3 for something something. Okay, how do you prove that it's discontinuous? Well, there are a few types of discontinuity. First, there is a removable type. So removable like this, there's a hole in between and then it continues on. And there is a jump discontinuity. So you stop at a hole and it jumps up to another point. And then the third one is, like an infinite discontinuity. So let's call this 1, 2, and 3. Now, in each of these cases, you have to prove that it's discontinuous in different ways. But in general, there are just two things that you need to take care of. First, we always want to talk about whether the left-hand side and right-hand side go to the same number. So first, we have to prove if you want to prove that something is continuous, the left-hand side and right-hand side must go to the same number. So if it's continuous, let's write that. If it's continuous, then first, the left-hand side and right-hand side must go to the same number, meaning limit as x goes to, let's say, a from the negative side of f of x has to equal the limit as x goes to a from the right-hand side of f of x. Meaning the left-hand side and right-hand side will come to the same point. So then this means that limit as x goes to a of f of x exists. So at least they're going to the same number. So for example, number 2 case, the jump discontinuity. You can see that the left-hand side and the right-hand side are not going to the same number. If they're not going to the same number in the first place, obviously it's going to be discontinuous. So that is the first thing to use to prove that it's discontinuous, or to check to see if something is discontinuous or not. Now, let's look at case 1. Left-hand side and right-hand side do go to the same number, so the limit does exist, except that there's just no number at that point. So then how would we say something is discontinuous at that point? So if something is continuous, it must have to meet 2 conditions. First, the left-hand side and right-hand side limit must come to the same point, meaning the limit at x equals a exists. The second thing is, if it's continuous, the second part must also be true, which is that the limit as x goes to a of f of x must equal whatever that number should be at a. And so if you look at the first case, the left-hand side and right-hand side go to the same number, so first condition is check. However, there is a limit, but at that point, nothing exists. So then this fails, which means it's discontinuous. So to prove that something is continuous, both of the requirements have to be met. So if you want to prove that it's discontinuous, it just has to fail one of them. And then number 3 is a special case, which we will talk about on the next page. Okay, so let's go back to this question. How do we prove that something is discontinuous, or how do we prove that this is discontinuous? So the fastest way is to graph it and see what we're looking at. This graph, if you graph it, you're going to see something like this. And you may be very tempted to say that it is continuous. However, let's look at what the numbers are. This function, if you recall from Algebra 2, you can factor this, and this is divided by x minus 3, which means this cancels, creating a hole. Now, where is the hole? The hole is when you take the leftover function and then you put in that actual value, which is x equals 3. So 3 plus 3 is 6. So that tells me that there is actually a hole here at 3, 6. The second condition says when x is 3, y is 2. So there's actually another point here. So what do you think? Is this continuous? Definitely not. There is a hole. So what kind of case is it? 1, 2, or 3? So it's definitely 1. It's just that there's an extra point, but it doesn't really matter. It's discontinuous by removable discontinuity anyways. So how do we prove that it's discontinuous? Well, if you want to prove that it's discontinuous, you just have to fail one of these. Okay, so left-hand side, right-hand side, do they go to the same number? Okay, left-hand side, right-hand side, they do go to the same number. And how would you know that? When you go from the left-hand side, basically it's just the number smaller than 3. If you look at the x conditions, smaller than 3 just means not equal to 3, because there's no other like less than or greater than. So just not equal to 3 includes less than or greater than. Okay, so the left-hand side is going to 6. Right-hand side is going to 6. So this satisfies. There is a limit. However, the second part, the limit has to equal f of a, meaning the limit as x goes to 3 of f of x has to equal f of 3. The limit as x goes to 3 is 6. The actual value at 3 is 2. So they're not the same, which means that this is discontinuous. So 2 fails. All right, let's have you practice. Does limit at x as x goes to 1 of f of x exist for this thing? If it does, give its value. If it doesn't, give the limit from both sides of the x value. All right, to prove that something is continuous or discontinuous, you just want to check two conditions. Limit as x goes to the left-hand side, right-hand side. They are asking for this. So then we're going to go to the left-hand side of 1 and then check the right-hand side of 1 and see if they go to the same number. If it does, then the limit at as x goes to 1 exists. Okay, so limit as x goes to 1 from the negative side. If you want to pause this video and try it and then come back and check, that would be a great practice. Okay, so x goes to 1 from the negative side. That is this one, x less than 1. So then you just put in 2 minus 1, which is 1. X goes to 1 from the positive side is this one, greater than 1, greater than or equal to 1, in fact. So then this is going to be 1 plus 1, which is 2. So what does that mean? Limit as x goes to 1 of f of x does not exist. All right. This one doesn't really want us to prove this continuity, and it's already discontinuous as is. It's a jump discontinuity, so that's pretty much it. It says if it doesn't exist, give the limit from both sides of x value. So then that's done. Both sides, one on the left hand side is going to 1, on the right hand side it's going to 2. Now let's talk about limit involving infinity. Okay, so there are two things. One is x going to infinity, and the other one is the actual limit is infinity. So let's talk about the first case, x goes to infinity. So this one says a limit as x goes to infinity, the limit is L. So the limit as f of x approaches L, as x approaches infinity. Sorry, just infinity. So that means something like this. If you have a graph, I don't know, like this, the question is, what is the y value when x is going this way? Okay, so we talked about this in probably chapter 1 where we were trying to analyze a lot of graphs. Okay, and the second one, x goes to negative infinity, y approaches L. So the limit of y approaches L as x approaches, let's just say negative infinity, and take this apart. So then this is when when x goes to the left, where does y go? That's the question. All right, let's look at this one. This is the second case. The second case where the limit is going to infinity or negative infinity, not the x. Okay, so this means as x goes to c from the negative side, y is going to infinity, or as x is going to c from the positive side, y is going to infinity. So there are two different things, again, we want to talk about. One, x going to infinity, whether it's positive or negative. Two, y goes to infinity, whether it's positive or negative. Okay, let's just put this in. So this first one here, this is the limit as x goes to c from the negative side. Y approaches, or f of x approaches infinity. And then when x is going to c from the positive side, f of x approaches infinity. All right, so let's take a look at this first question. So let's say f of x is this function, which is shown here. The question is, what is limit as x goes to infinity of f of x? So when x is really large this way, what do you think the y value is? So kind of look at this graph and kind of make your guess. Of course, you can drag this out more so you can see it better, but you can probably guess that it's going to go to 0, which is true. And you can do the same thing on the left hand side. So when x is going to negative infinity, the question is what is y? So when you go to the left, you can kind of see that it's also going to go to 0, which is correct. So again, this is when x is going left and right, you're looking at the y direction to see what number it's approaching. Now let's look at this one. This is the second example. So the limit as x goes to 0 from the positive side, where is y going to? Okay, so as x is going to 0 from the positive side, where is y? Well, y is going up, so we're going to say, infinity. Okay, and then the same thing, limit as x goes to 0 from the negative side, where is y going? Okay, as x goes to 0 from the negative side, you can see that y also goes up, so we're going to say infinity. Now, there is a note on this. Infinity does not mean that there is a limit, so we can't just say that, yeah, it's going to infinity, and infinity is a number. Infinity is not a number, it's just unbounded or a super large number. So then it just means, so another way to say that is we say the limit does not exist. Okay, so we would say does not exist. Instead of thinking that it's a number. On the test and things like that, you can put both, and it's understood that when you say infinity, it just means the limit does not exist. But try to just remember that both of them mean the same thing. All right, so let's practice. So what I want you to do is graph these in your calculator or decimals, and then try to figure out what these limits are. Okay, so based on what the x value is telling you to do, try to figure out the limit. So go ahead and pause this video and then come back and check your answer. All right, let's check your answers and see if you got all of them. The first one's pretty easy. It's very clear to see that when x is going to infinity, y is going to infinity, and when x is going to negative infinity, y is going to 0. The second one, when x is going to 2 from the negative side, y goes down, so then you can say negative infinity, or you can say does not exist. On the right hand side, when x is going to 2 from the positive side, it's going up to positive infinity, or you can say does not exist. Number 3 is a little bit tricky. This is a logistic function, if you recall. So the function actually looks like this. If you didn't extend your graph enough, you may not have seen there is a upper bound. So when x is going to infinity, it's actually going to 50, which is this number. So make sure you zoom out enough so you can see it, or try to recall that this is the logistic function, and then so you can be aware of what you're supposed to see. And then when x is going to the left hand side, y is going to 0. And then the last one, when x is going to infinity, y is going to infinity. When x is going to negative infinity, it's going to 1. So be careful on that.